This is our final project presented to you by Angel Hernandez and Naimur Rashid. The first condition of our function is that r of x should be in the form of r of x equals f of x over g of x, and where f of x and g of x are both polynomial functions. This condition is true for our function r of x, which is x squared minus 7x plus 12 divided by x squared minus 9, which are both polynomial functions. F of x and g of x have two rational roots. For f of x, we find that negative 3 times negative 4 equals 12, and negative 3 minus negative 4 is equal to negative 7. And for g of x, that 3 times negative 3 equals negative 9, and 3 minus 3 equals 0, giving us the two roots for both functions. For f of x, it's 3 and 4, and for g of x, it's negative 3 and 3.
So for the third requirement, we see that our function, r of x, does have one rational root, and we find this by setting the function equal to 0, and then we just factor it out in order to take away the x minus 3, which leaves us to having to set the numerator to 0, which is just x equals to 4. So for condition number 4, we see that we need a vertical asymptote in our function, and we can find this really easily by only having to deal with the denominator in order to find the vertical asymptote. And so we just factor out the denominator and we find ourselves with two answers, but there's only one real answer. And we can see this in the graph simply, that there's only one real vertical asymptote. So for condition number 5, for a function, we need to have a horizontal asymptote as our end behavior model. And in this function, all we need to do is look at the degrees, and since the degrees are the same in our function, we look at the coefficients, which are also the same, so it just be 1. And the thing about this function in particular is because it needs to be an end behavior model, as x approaches infinity, the asymptote will be 1. So for condition number 6 of our function, we need to have a removable point of discontinuity. And for our function, we went with a hole that's located at x is equal to 3. And in order to remove the point, we need to find the limit as x approaches 3. To do this, we need to find a way where the denominator won't equal 0. So we factor out the numerator, we factor out the denominator, we see that x minus 3 cancels each other out, and what we're left with, we can just plug in 3, and we get our answer, which is negative 1 over 6.
This is our graph of r of x. There's a vertical asymptote at x equals a negative 3, and a horizontal asymptote at y equals 1. The limits for both our vertical and horizontal asymptotes are undefined because the left and right hand limits don't match. There's also a removable discontinuity at 3, negative 0.1667. The limit for this discontinuity as x approaches 3 is negative 1 over 6. We'll go more in depth about limits in our next section. In this section, we'll be talking about our three limits. The limit as x approaches infinity and negative infinity for r of x is 1, because the leading powers are the same as well as the leading coefficients, giving us 1 over 1 for both limits as x approaches infinity and negative infinity.
So here we have the last limit, which is as x approaches negative 3. And this is a really special one because this deals with the vertical asymptote. And we want to see if we can find the limit as x approaches negative 3, but if we just plug it in or factor it out, it doesn't exactly work in our favor. So what we can do is check a really close number that's below it, so it's approaching from the right, and a close number that's above it, it's approaching from the left. And so we do this and we plug the numbers in, and in this case I plugged in negative 2.99 for approaching from the right, and we got a number that's positive on the numerator and negative on the denominator. And for negative 3 approaching from the left, I plugged in negative 3.01, which is a positive over a positive. This means that the left and the right hand limits aren't going to be equal, because no matter what way we think about it, they can't exactly be equal if one's negative and the other one's positive, so the limit does not exist.
To We will now discuss the first and second derivative of r of x. Finding the first derivative was quite easy. We just used the quotient rule on r of x, and we found that the first derivative is 7 over x plus 3 squared. Finding the second derivative was even easier. We took our previous answer of 7 over x plus 3 squared, and we applied the power rule, and we got negative 14 over x plus 3 cubed.
So let's go ahead and take a closer look at the graph. We've shown you this graph before, but let's take a look at where the intercepts are. The y-intercept is at 4, 0, and the x-intercept is at 0, negative 4 over 3. And there's nothing really too fancy about these, just regular normal intercepts. Another thing to note is that the function is always increasing. It's never decreasing. It's always going up from here. And another thing to note is it doesn't concave up or down. There's no extrema. Luckily for our function, it's pretty simple. Now for our MVT problem. In our problem, we want to find all of C that exists in the interval of negative 4.75 to negative 3.778 within our function r of x. And all it needs to do is satisfy the MVT. Now, there are two things we have to do before. We need to see if r of x is continuous within our interval, which it is, and that r prime of x exists within that interval, which it does. So, what we do now is we want to solve for r prime of c. And the way we do that is by just finding f of b minus f of a over b minus a, and we find f of b, which gives us 10, and we find f of a, which gives us 5. And then we just plug all the numbers into the equation, giving us 5.14, and then from there, we set the derivative of our original function set to 5.14. We do the math, and we're left with two answers, but only one of those answers actually fits within the interval, and that is negative 4.16. And if we were to plot the tangent line in accordance to that point, we could see that the secant line of the given interval of our function is actually parallel to that tangent line.
We'll use the root 4, 0 on the interval 0, 6 to prove that the root exists. Since this interval is continuous, we can use the intermediate value theorem. When we plug in 0 into r of x, we get negative 4 over 3, which is less than 0. When we plug in 6, we get 2 over 9, which is greater than 0. Therefore, guaranteeing that there is a point in between these two that makes r of x equal 0. We restrict r of x's domain over the closed interval 0, 8. When we plug in 0 into r of x, we get negative 1.333, which is our absolute min. When we plug in 8 into r of x, we get 0.364, which is our absolute max. The minimums and maximums are the endpoints because there are no critical points.
Finally, we have our tangent and normal line at any given point, and we chose at x is equal to 4. Nothing special about it, just a regular old point. First thing we want to do is find our y. And we do this by plugging in 4 to the original function, and doing the math, we get 0. So our point is 4, 0. Next, we want to find the slope. To do this, we use the derivative, because remember, the derivative is the slope at any given point of the function. And so we already know what the derivative is, and we plug in 4 into it, and we get 1 over 7. Then we plug that into our equation, y minus y1 is equal to mx minus x1, and we get the slope-intercept form, which is y is equal to x over 7 minus 4 over 7. Then we want to find our normal line. This is much easier because we already know the slope of the tangent line. And to find the slope of the normal line, all we need to do is negative 1 over the slope of the tangent, which just leaves us with the slope being equal to negative 1 over 1 over 7, which is just negative 7. Then we leave this in the point slope form, y minus 0 is equal to negative 7, x minus 4. Simple. Let's take a look at a sketch of our function in comparison to the tangent and normal line. Our function is the one in red. Simple, we've seen it many times before. And we see the point 4, 0, which is the point we found at x equals to 4. Our tangent line is in blue, which crosses that point, but doesn't touch any other point. We can see that clearly. And then we also have our normal line, which is in purple. Cool.
Alright, that concludes our presentation. Thank you.